your x cubed, x to the fifth looks the same but skinnier. X to the fourth, what's that? Parabola, a little skinnier than the normal parabola. Bless you.
Bless you.
What's x to the sixth? Another parabola. It's just getting skinnier each time, isn't it? Okay, so what we're seeing is these graphs have some similarities. Which ones look the same? Evens and odds. Okay, so this is what we're going to call end behavior of a graph. So f of x equals x to the n resembles what if it's an even power? What is it going to look like when you have an even power? A parabola. I'm going to put x squared. And what does it look like when it's odd? The chair, x to the cube. Okay, so all of the ones, x squared, x to the fourth, x to the sixth, x to the eighth, they're all going to look the same. If that power is even, then it's parabola shaped. If that power is odd, it's going to look more like our chair. What is the difference as that exponent becomes larger? What happens to the graph?
It gets skinnier.
It what?
It's skinny.
It gets skinny. It becomes more narrow. Okay. So our graph narrows as the exponent goes up. Alright. So our end behavior is what happens as the graph becomes large in the positive or negative direction. It is always going to be determined by the leading term. So that's just the term that has the highest degree. Whether it's the first thing listed or not, doesn't matter. You just look at the term with highest degree. If the leading term has even degree, that's when we said it looked like a parabola. So as long as it's a positive x squared, x cubed, x to the fifth, our end behavior is up, up. Both ends are pointing up. If you throw a negative in front, negative x squared, negative x to the fourth, what happens? It flips it down, so both ends are going to be pointing down. Okay, so positive coefficient, you're looking at parabola, negative coefficient, just an upside down parabola. When I ask you end behavior, we're really just going to be drawing these arrows to show the direction the ends are pointing. If the leading term has odd degree, if it was a positive coefficient, it looked like x cubed, so my ends were down, up. The left one's pointing down, the right one's pointing up. If you throw a negative in front, what would it do? Up, down. Alright, so we are just going to practice finding end behavior of graphs. Now, if you absolutely had to, could you graph it and look at the graph and see? Absolutely. But we're going to be doing so many of those, we'll probably get used to looking at it and just having an idea in our head of what it should look like. But if you need to, you could definitely graph it and check the graph. So let's find the end behavior. If I give you 4x cubed, what are you going to look at in this? We just need this part. It's an odd degree, so that means it's going to look like a chair. Positive coefficient, so it's the normal chair. So what's my end behavior? Down, up. Okay, second one. What's my end behavior going to be? Down. It's an even, so it's a parabola. That means the ends are doing the same thing, but the negative flips them, so it's going to be down, down. Is it as obvious what our degree is here? No. So we could go through and multiply this whole thing out, but that would be very time consuming. Agreed? All we really care about anyway is that leading coefficient. So we could quickly find the leading coefficient. If you're just taking all your highest powers of x, we have a 3, this one's an x, this one would have x squared. So if you just multiply those pieces together, what do you get? 3x cubed. So now can you tell me your end behavior? What would it be? I don't know. Odd degree, positive coefficient. The last one. Let's talk about if we just multiplied the x's together. We had the 1/2. This is an x squared. Alright, if you have x squared cubed, what would you do with those exponents? Multiply, so that would give us x to the 6th. This last one would give us x to the 4th. So if you multiply all that together, you get 1/2 x to the 12th. So what's your end behavior? When in doubt, how would you find your end behavior for that graph? Graph. You have a graphing calculator. You could plug it in and just look and see what the graph does. Questions there? I think the next slide on here, we're just going to find a polynomial that would work. So we're not going to multiply it all out or anything. We've had some questions before that said find a polynomial. So it's the same type of thing. When I give you the degree, what is that telling you? How many x's you have. If you multiply it all out, it's the highest power. If it's in factored form, it's how many total x's. Okay, so if I want this polynomial, -3 is a 0. So what goes in my polynomial? 2 is a 0. And 5 is a 0. Is that degree 3? Yep, so I'm done. There weren't any other stipulations here, so I don't have to do anything else. Okay, the second one. If 0 is a 0, what are you going to put in your polynomial? X. It's x minus 0, which is the same as x. If 4 is a 0, we have, okay, and if 12 is a 0, okay, what's the degree of that? Right. This is only degree 3, but I told you it had to be 4. Now I can't give it any new zeros, so what could I do to make this a higher degree? Yes? What'd you say, John? Square something. Did I tell you which one had a multiplicity of 2? No, so does it matter which one I square? No. But if you throw a square on one of these, then you have 1, 2, 3, 4 x's. So that would take care of our problem. I just said find a polynomial that works. I didn't say that there's only one. I know. If I'd given you a multiplicity, then it would have to go specifically on which one has a multiplicity of 2. But on this case, I did not. Alright, this one, degree 3. If -1 is a 0, what goes in here? If 1 is a 0, if 2 is a 0, okay, do I have my degree 3? Y-intercept is 1. What does that mean? Yeah, there could be something else out in front. A y-intercept, this is like the point 0, 1. If I plug in a 0 for all of my x's, this whole thing has to equal 1. So that means 2a equals 1. So my a is 1/2. So 1 times negative 1 would be negative 1 times negative 2 is 2a. So this side is 2a, the y-intercept is 1, and I solve for a. Other questions?
Terminology-wise, if you have a polynomial, these things are equivalent. Saying a number is a 0 is the same thing as saying x equals c is a solution to p of x equals 0. In other words, when you make your x equal that number, your y is going to be 0. Or you could say x minus that is a factor. In terms of a graph, that means it's the x-intercepts. So if I say find the zeros or the x-intercepts, you're looking for that number that makes it touch the x-axis or makes the y value equal 0. If I ask for the factor, that's when you do x minus the number. So if I gave you this problem and asked you to find all the zeros and their multiplicities, how would I find my zeros? I've done it before. What do you have to do? You're basically finding all the x values. Does 5 ever equal 0? What makes x minus 2 equal 0? What makes x plus 3 0? But it was squares, so that's a multiplicity of 2. What makes x minus 1/2 0? 1/2, this one was to the fourth, so multiplicity of 4. You guys do eat. So we have this x out here. What's that going to be? 0. X plus 1, negative 1. 3x minus 2, and that was cubed, so that's a multiplicity 3. And x minus 5. 5 multiplicity 5 because it was to the 5th power. Are we okay with that? These multiplicities are going to become very, very important to us. Tomorrow we're going to start graphing these polynomials. And the multiplicity actually has a lot to do with what happens on the graph. So if you have an odd multiplicity, so you have some 0, if it has an odd multiplicity, what that means is when we graph it, we're just going to go straight through the point. But when the multiplicity is even, your graph is going to hit it and bounce off. So we'll be talking a lot about these different zeros, and I'm going to say, okay, does the graph go through or does it bounce? You have to look at the multiplicity. Odd multiplicity will always just go straight through, and even multiplicity is going to hit it and bounce off. I think that was the last slide I printed for you, wasn't it? No, I printed the whole thing. Okay. We're going to go over just a few more pieces today, and then I'm going to give you enough time to do your homework towards the end. We know now how to determine the end behavior of a graph. And we know, looking at the zeros, we're going to decide if it bounces or goes through, and we know that's based off the multiplicity. Another thing we're going to talk about on our graphs are turning points. Turning points are where your graphs change direction. And so it is based on the degree of that polynomial. So the degree is your n, that's your highest power. It says a polynomial degree n has at most n minus 1 turning points. What exactly does that mean? What would a turning point be, do you think? If you had to guess. Okay. It could be the c, the 0, the x-intercept. It doesn't have to be, but it could be. When I'm referring to a turning point, I'm talking about my graph changing direction. So if I looked at this particular graph, how many turning points does that have? 2. So what would the degree have to be? 3. Your degree, the degree n has at most n minus 1 turning points. The most turning points you can have is one smaller than your degree. So if you have 2 turning points, it has to be at least x to the 3rd. Now it could be bigger. It could be x to the 4th, x to the 5th, x to the 6th, but that's the smallest. These turning points are right here. What's another name we could give for those? Those are maximum and minimums. So maximums and minimums, turning points, it's just where your graph is changing direction, and it's based on your degree. So this is just saying the reverse, like we just did here. If you know the number of turning points, you can determine the smallest possible degree. So if I graphed, like, I drew this. Could this be the graph of a negative x squared? The end behavior graph matches x squared, but what's wrong with it? I have 3 turning points, so this would have to be at least an x to the 4th. Does that make sense? Now just kind of another. This one could be x squared. Could it also be x to the 4th? Yes. You could have a degree higher than that. It just gives you your smallest possible. All right, any questions on your turning points? So tomorrow we are going to talk all about graphing these things. I think this is really where I want to stop today.